For the kind introduction, and thanks to the organizers for inviting me. It's really a pleasure to be here. I was here before some years prior, and some of the talks I listened to helped to shape my career. So I'm quite happy to be back here on the other side of the room. So this is a picture or a rendering of a transition metal Janus halide, and this is a cover of Advanced Theory and Simulation back in 2023. And some of the work I'll talk about is coming from this cover article, which we're the co-authors of, me and some folks in my group, including Professor Kaxiras. So the title of the talk is Accelerating the Discovery of van der Waals Quantum Materials Using AI. And like beginning this kind of chat with setting out kind of from a very big picture what we're aiming to do, which is combine materials experiments and theory in the form of digital data alongside statistical methods and computational tools to accelerate quantum materials discovery. And what I mean by quantum materials are, in particular in this case, maybe materials that are suitable for quantum computing, magnetic memories, have some sort of common phenomena like a superconductivity, or will be the main focus of this work is long-range magnetic ordering. Like you think of a ferromagnet or anti-ferromagnet, you think of your ferromagnet, for instance, but with maybe potentially more exotic properties. I also like beginning with a definition, although depending on who you ask, this definition will change. But I like to think of AI as, or machine learning as being a part of AI, where AI includes machine learning and robotics and control, although people are using AI for meaning deep learning these days, but I don't like it. But this is my definition. And it intersects with data science, which comprises databases, data mining, data visualization, and also statistics. I'll ignore that thing on the, what does that say? Update now. Okay, well. Doesn't show up here. Oh, let's ignore it. Not sure how to, oh, it's on the other. Okay, thanks. Okay, so the outline of the talk, I'll start with the motivation, which will involve challenges for materials discovery. Then I'll propose some ways to overcome those challenges, which include materials informatics. And I'll have 3 use cases. I'll spend most of the time on these van der Waals magnetic materials. These are kind of like sheets of atomic materials that could be thinned down to the monolayer. Think of a single atomic sheet of atoms, and you can comprise many layers to make a so-called van der Waals bulk heterostructure or material. That'll be the first bit. And these will be intrinsically magnetic. And those are kind of exciting because they're kind of new since 2017, I think. Then we look at these topological magnets. Topological materials are interesting because of their transport. There is this idea of thing being topologically protected, and the archetypical example is to talk about like how a coffee cup with a handle and a donut are topologically the same. I won't show this picture here, but the example I'll use maybe is if we have a material and it is, say, a topological insulator, then it'll have transport along the edges of the two-dimensional material, van der Waals material, but be insulating in the bulk. And if you have like a chunk of some like a crystal, it's 3-dimensional. You can have transport on the surface, but not in the bulk, in the middle of the material. These are these topological materials, and they can also be magnetic. So they're topological magnets. And then you can start taking different sheets of these 2D materials or van der Waals materials and stacking them in different ways to make new materials. And these are these heterostructures of van der Waals materials, which I'll talk about last. The last 2 will be kind of brief. I love this slide. This is taken from a paper titled "More is Different" by P.W. Anderson. This is an electron. Electron has spin. This is a collection of electrons. And the idea in this paper, "More is Different," is that a collection of particles can be more than the sum of the individual components. So you could start looking for emergent phenomenon in these systems that won't exist just looking at an individual component of the system. For instance, you can ask, under what conditions do all the spins in the system give rise to long-range ordering, become ferromagnetic, for instance. And the big question is, can AI take some component of the system or the properties of a component of the system and predict something about the emergent phenomena, which is an exciting open question. We'll try to address part of that later today. So these electrons can live in these 2D atomic crystals or these van der Waals magnetic materials. This was discovered chromium triodide. This is a crystal structure. So these are the chromium atoms are sitting here, and the iodine atoms sitting 3 above and 3 below the plane. This is kind of a top-down view of a part of the chromium triodide crystal. And over here is again a part of the chromium germanium telluride crystal. These are the chromium atoms. This is germanium here and here. This is tellurium above and below the plane. And these are so-called MOC or magneto-optical Kerr effect spectroscopy measurements, basically showing that down to 1 layer of this material, you have a ferromagnet, and down to 2 layers of this material, you have a ferromagnet. And this is new and surprising and is discovered as recently as 2017 by Pablo at MIT down the street and some group, I forget the PI's name, in the West Coast. It so happened I was working on chromium germanium telluride with Amir Yacobi at Harvard and doing experimental measurements using ferromagnetic resonance. And the issue I had is that the resonance of this material was outside the range of the material of the equipment that I had. So I needed to have either better equipment, which was hard to come by, or different material. And also this material is quite air sensitive. And so I needed to find a new 2D material that was magnetic. And at the time, 2016, which I did at the time I was doing my experiment, 2016, no one really knew where else to look. And so this interest in finding new 2D ferromagnets kind of sparked this interest in mine of doing a computational search for new materials. So that's what I did. And so by Waals, we study magnetism 2D materials. There's this idea of emergent phenomena, which I alluded to before. And then there's this Merman-Wagner theorem, which basically says you shouldn't have long-range magnetic ordering in 2 dimensions unless something is breaking the symmetry. And that thing is a magnetocrystalline anisotropy, which just means that the magnetization vector points more readily in one direction, say in plane, in plane versus like out of plane. So you can imagine some interesting physics arising where you make 2 or 3 layers or 4 layers of this like van der Waals monolayer, and then you vary its magnetocrystalline anisotropy, and there could be this interplay between this thing that's breaking the symmetry and the reduced dimensionality, maybe giving rise to some interesting new physics, maybe something to explore. And there's some applications in data storage, which I'll talk more about in this next slide, stolen from our friends at IBM Research. This is talking about magnetic random access memory. And the key idea for this slide is that advances in materials drive technological innovation. So in the 70s, this idea for MRAM was developed at cryogenic temperatures. So I think at liquid nitrogen, 70K or so, or I'm not exactly sure the temperature, but cryogenic, well below freezing. And so the idea is if you can encode bits, ones and zeros with spins parallel and anti-parallel. It took 20 years for you to have this kind of device at room temperature, and many more years with advances in the tunnel junction of the material of the device to have better read speeds and spins going from in plane to out of plane to have improved write speeds. So 30 years or a bit more than that to have a going from kind of lab to fab where you have the idea to something industrially relevant. So that's a long time, 30 years. And IBM folks are smart. So why did it take so long? Well, materials discovery is quite tough. And we like to have this process happen in 30 months or 30 weeks or some smaller time scale. So again, it's challenging because you have to identify the materials with just the right properties. In this case, you have to find materials that have magnetic order. Of course, you need to have multiple criteria satisfied often. So to be industrially relevant, you should be having a screw temperature at above 300K. Curie temperature is a temperature at which the spins align, above which they will be randomly aligned. And one key idea is that there's this estimate for virtual chemical space, suggesting that, or claiming that there are 10 to the 100 candidates for materials in the universe, including small molecules, large molecules, and crystal structures. This is really an enormous number. And to give it some perspective, it's the number of observable particles or particles in the observable universe. So I like to make this analogy between exploring space and exploring a material space or chemical space. Okay, so I went too fast. So imagine like before November, I think 2022, if you wanted to find something, anything, maybe a recipe for banana bread or directions to go to the movie theater, what would you do? Yeah, you've seen it. You would ask Google. Okay, but what if you ask Google for undiscovered 2D magnets? It'll probably explode or start smoking. We wouldn't get a reasonable result, but you could probably guess that post November 2022, there's this advent of a rise of ChatGPT. We have this promise of artificial intelligence. We've already had a few talks that used ideas from ChatGPT, LLMs to do interesting like materials physics, or just do interesting science, combining big data and AI with science. And the great thing about ChatGPT, which already is a human-like chatbot, is that it encodes the text in a special way. And I like to argue that there's advances in the data representation that led to its great success. So encoding the text in some special way allowed you to have ChatGPT be successful. And I won't talk about ChatGPT very much, but I will come back to this point that data representation of the materials is super important. And there's some experts in the room on that. And I think you'll hear a talk more about that in the next talk by Tess Schmidt in the audience. So AI is really exciting. You do really interesting things, as you probably know. This is a image recognition model called You Only Look Once, or YOLO. It can classify moving images in real time, identifying a bike or a car, a person, and so on. So the question you can ask, can you apply these powerful tools to study materials? Can you take a lattice of carbon atoms, graphene, and tell, without doing measurements or calculations, just by inspecting the crystal structure and chemical composition, telling that it's conductor or metallic, or look at MOS2, tell that it's a semiconductor, or chromium germanium telluride, chromium triodide, and tell that these are van der Waals ferromagnets, or manganese bismuth telluride, and tell that that's a topological insulator that's also ferromagnetic. That is the question. So the goal is to use this thing called materials informatics, which I'll explain a bit in a second, to do material discovery. And we'll focus on, in the first part, finding new 2D magnetic materials or van der Waals magnets that are chemically stable and have a particular magnetic order. In particular, they should be ferromagnetic, just to pick an order. And hopefully do some knowledge discovery. This is harder. Can we extract physical insight by using these tools, examining, for instance, latent space of an autoencoder or some other hidden layer of a neural network to learn something about the physics? That's tougher, but we'll give it a little example towards the end. So what is material informatics? It's this combination of artificial intelligence and material science, where the AI tries to approximate some function f of x, which takes as its inputs x1 through xn. These can be things like chemical properties of the elements in the periodic table, like the number of unpaired electrons, number of valence electrons, the atomic number, and so on. This n can grow quite large. So there's an advantage of recognizing patterns in the data that a machine can do easily, but our human brains have challenges to do. Also, this function can be evaluated very quickly, giving you a fast prediction of y, typically things that are hard to calculate or measure, like the magnetic moment. Or this can be evaluated in milliseconds on a laptop once it's trained, and doing the experiment or the first principles quantum simulation on a classical computer can take days or months, depending on the thing you're trying to investigate. Okay, why do you want to use AI? Well, we talked about material search space being really huge, 10 to the 100 according to some paper describing virtual chemical space. Something more concrete, there's the so-called inorganic crystal structure database, which has over 200,000 inorganic compounds. There's also the chemical abstract service, which has 49 million entries of inorganic and organic compounds. And there's a virtual chemical space. So you can imagine sifting through this space, doing serial calculations or experiments would be quite challenging. Now, most of material science applied to AI, materials informatics, doesn't really deal with a lot of big data, but that's maybe not entirely true, depending on how you pose the problem. Of course, 200,000 is not, I would say, maybe not big data. Maybe 49 million is. This certainly is. And I like to say that there's this distinction between labeled and unlabeled data. So in cases where we have the crystal structure, but we don't know anything about its characteristics or its properties, these are unlabeled data. And when we have a database and all the characteristics, say the magnetic properties are known, these are so-called labeled data. I'll come back to that in a little bit. Okay. So this is a picture of a crystal. It can be one of two choices or popular or likely choices. Which one do you think it could be? Is it? It's kind of, it could be glass. That's okay. Three choices. It could be glass. It's a diamond. Yes, it is a diamond. But maybe that's not an easy guess because typically diamond is. What's that?
Could also be ruby or.
It could be ruby. Yes, that's
Usually cut different.
that's the usual. Oh, okay. I didn't know that. But ruby would be my first guess. It turns out it's diamond. Now, why does diamond have this strange color? Because it has these defects, meaning you replace carbon with nitrogen, and near to it, nearby, you have a vacancy, no carbon atom. So this is nitrogen vacancy defect. And if you have many of these defects, you get this deep red color. So I like to argue that there's a structure property relationship, which you can see in this case. We'd like to have an AI learn that structure property relationship and exploit that relationship for quantitative predictions. Another example is take this hexagonal lattice of carbon atoms and this hexagonal lattice of boron and nitrogen atoms. You have graphene over here on the left, boron nitride on the right. Turns out that graphene is a conductor and boron nitride is very much an insulator, a wide bandgap insulator. And the lattice is the same. The lattice is decorated differently. And then you change the chemical composition and the structure or the properties change drastically. So can we learn, again, in this case, the structure property relationships for these materials? One of the papers that got me really interested in doing this many years ago was this paper studying ferromagnetic transition metal alloys. And in this case, they took different transition metal alloys. Some are ferromagnetic, such as these open squares. You zoom in, you can see them clearly here. There are also these non-magnetic alloys, these black squares here and here. And this zoomed in portion really shows clearly that you have a certain region of your two-dimensional descriptor space with available atomic volume on the x-axis, one dimension, and the next dimension on the y-axis is calculated chemical hardness. Not the physical hardness, but it's an electronic property of the electrons. You find that there's this region where there are only certain type of ordering, ferromagnetic ordering of your alloys. So why is this important? Well, you see the pattern with your eyes. If you have some new material here, you can quickly guess or make a prediction of what ordering that would be, and what would you guess this should be? Is it non-magnetic or ferromagnetic? Some people.
Black squares.
Yes. So it should be like the black squares, which should be non-magnetic, exactly. And if it's here, you probably predict that it's ferromagnetic. And this simple idea is what you can ask a machine to automate, make these predictions based on the structure in the data, or the patterns in the data. So we'll do something similar later on. And one thing we should keep in mind is how do we choose a descriptor in a careful way? In this paper, they chose these based on their domain knowledge, and it worked well for these alloys. But in general, maybe you have a different way of describing the data. It's non-trivial. So how do you choose these inputs to your function that your AI approximates? What is a good choice for the materials descriptor? So we'll come back to this in a bit. Okay, so there are kind of three ingredients for materials informatics or maybe machine learning. First, you need data. We all know data exists in the cloud. I got a few smiles. We have also descriptors. These are the mathematical representations of the materials, and the statistical models over here on the right. Data are really databases are accessible these days. Many groups are building their own databases. Also, many groups are building nice mathematical representations of materials. One of the early ones were Coulomb kernel, vagabonds, and SOAP, smooth overlap atomic positions. And there's these ones based on graph neural networks. I should have added here also these equivariant neural network models, which you'll learn more about in the next talk given by Tess. And there are groups like Google developing these very nice data science tools which you can use. They're powerful. We download them to a laptop and makes life quite easy for implementation of these statistical models. So for the data, we have different databases. The materials product is perhaps the most popular of all of them. And there's AFlow, C2DB. This is one just based on 2D or Van der Waals materials. We have Nomad, ICST, which you've seen before, MacNavi. MacNavi is a database that's set up by NIMS. I worked at NIMS in Tsukuba, Japan for a few months. There's Jarvis coming out of NIST, IDA, and the materials cloud. So there are quite a few databases, and there are many more that I haven't shown here that already that also exist. And the new ones are actually have more entries and are quite exciting. So there's this idea of descriptors. This is again some description of the material. It can be something as simple as the atomic properties of the constituent elements. It's a very simple-minded descriptor. You can do something more sophisticated, like build an equivariant graph neural network, or do something like a graph neural network, or do something like SOAP, which I'll describe a little bit later on, a little bit more detail. And there's a third point I'd like to add is this learning representation from the data themselves. I think that's a super important thing, which is maybe linked to these foundation models and LLMs, but I'll give particular materials science perspective on that. Okay. Physical models can be something as simple as a linear regression, something as sophisticated as some many layer neural network. And we'll talk about a flavor of neural network in a few slides, allowing us to implement or AI model that maps from the inputs to the magnetic properties. So the typical material discovery framework involves starting from a large set of materials candidates, and we screen by these material simulations on a classical computer, and then verify with experiments some subset that have properties we're interested in. And then in the end, hopefully we get a desired set of materials with the target properties. And typically this takes a time and is expensive, and experiments take longer and are more expensive. In the past 10 years or so, AI is becoming this really nice tool to speed up this process, accelerating the overall materials discovery process. But even though it's fast and inexpensive, it has lower accuracy typically. You need often pre-existing data to train it. So there's some challenges in this space, need for accurate data sets, lots of labeled data where you know the target property. So you can have the crystal structure, the NaCl, for instance, exists, but you may not know anything about its properties. So you don't know its label, so it's unlabeled in that case. But if you know, for instance, it's salty, then you know a label for that material, and that becomes a labeled part of the data set. So the solution I propose in the first part is to do so-called semi-supervised learning, also called self-supervised learning. I'll explain what that means in a little bit. So the first step is to create data, and we use these material simulations to do that on a supercomputer by taking our typical material, chromium triiodide, and we would decorate the A sites here with different transition metals shown here, and the X sites, the iodine above and below the plane with different halogens. If you do that, we get about 10,000 or so potential candidates. We chose about 700 at random, for inspection with these materials simulations on a supercomputer, which took us, I think, 3 years or so. So we don't want to do 10,000 on a supercomputer. It'd take us very, very many years. I'll still be working on it probably. So we stopped at 700 and we tried to build an AI model to predict the other materials' properties. We considered ferromagnetic ordering and anti-ferromagnetic ordering of the materials. For instance, we already found that chromium triiodide is a ferromagnet. Turns out iron trichloride, just by changing the chemical composition of the material, becomes an anti-ferromagnet. I think that's pretty remarkable. It's hard to predict just by looking at the chemical composition what the magnetic properties will be. At least I can't do it. So we're asking, we can calculate using DFT, but if you want to really predict 10,000 of these candidates, you need something else to do it, something like AI. So here's some results with the A1 substitution on the horizontal axis, the A2 substitution on the vertical axis. The color here is now the magnetic moment, which is like the magnetization. There are these gray squares, which are missing data, materials where we don't have data for, don't have these material simulations calculations for. To give you an idea, each square is different material. So this one is chromium 2. I forgot to say both X sides for this panel are iodine. So this is chromium 2, I6, or chromium triiodide. Notice that there are patterns in the data. We like the AI to learn the patterns for quantitative predictions. We also care about chemical stability. This just means you want to be able to make the material in the lab, so it should be stable once you try to make it in the lab. And a rough proxy for chemical stability is a thing called formation energy. And if it's above 0, you know for sure that you can't make it in the lab. If it's less than 0, you know you have a chance. It's not a guarantee, but you have a chance. And again, we have A1 substitutions on the horizontal axis, A2 substitutions on the vertical axis, and each square is a different material. And again, they're missing data here. And in this slide panel, they're now both mixed X sites. There's both chlorine and bromine here. This is a so-called Janus Phoenician metal halide. Okay, so we have some data. Then we need some materials descriptor to describe our data before we can do any machine learning on it. And the descriptor I chose for this study was the smooth overlap of atomic positions, kernel, or SOAP. And SOAP, the way it kind of works qualitatively, if you have a lattice or of atoms, you go to a particular atom, a particular site, and you look at its chemical environments, and you create some vector of numbers by linking that site to its neighbors. Then you go to the next site and you repeat that. So you get a matrix of numbers which encode all the sites and their chemical environments. Then you unwrap that into a very long vector, and you can project that very large vector into 2 dimensions using PCA or something like T-SNE. And you get some interesting things arising. You notice all the crystal structure types are clustering. For instance, the diamond structures are over here, hexagonal structures are over here, and each point is a different material, and it varies by chemical composition in this cluster and also in this cluster. So the point is that the SOAP encodes something about crystal structure, how the atoms are arranged, and also their chemical composition, which atoms are in the material. The issue with this SOAP vector, which I think why it's maybe not used super often, is that it can be really high dimensional. So there's 98,000 dimensions in this SOAP vector. That's too many for us to learn with a small number of data in our data set. Didn't really work for 700 data points. And so we use PCA to reduce the space to about 220, and that seemed to work pretty well for modeling the data. So our input to our AI model is a PCA compressed SOAP vector, which we then can use to predict the formation energy and the magnetic moment. So we use this neural network model that implements semi-supervised learning, that's combining unsupervised learning, where you have a learning without any labels, and supervised learning, which is what people typically do, where you map some materials characteristics like atomic number to some property of the material like its formation energy. Models we'll use to do that are these autoencoder models and this feed-forward neural network model. We'll couple the loss functions, and this is how they look. This autoencoder over here is a cartoon of the autoencoder we used, and for the labeler network over here on the right. The nice thing or thing to point out is that the latent space created by autoencoder is fed into the input to our labeler network. This network doesn't need any labels. There's no y values associated with this, so it's unsupervised. And here, this is a supervised part, which gets trained on the y, which can be magnetic moment or formation energy. And if you couple the two, you have a semi-supervised learning. And the exciting thing about this framework is that if you add lots of unlabeled data without doing any additional work, any additional DFT calculations or say experiments, you can get a big bump in improvement of the prediction accuracy of the model. And that's because this latent space is getting better by adding more data. Representation is learned more accurately by adding more data. So typically you have a training data where you tune the coefficients of the model. For instance, you have these 6 data points. Let's say each one took you a month to measure or to calculate. You can then think about fitting a model. So you're learning a slope and intercept. This is your model. This is a toy example, by the way. And then to check your model, you might compare it against the test data, these red squares, data the model hasn't seen before. And in this case, prediction is pretty close to the actual value. It's exactly the value here and pretty close here. So you can claim your model is working pretty well because your predictions are very close to the actual values in both the training set and especially the test set. So what we can do is then collect our results, create a model, and compare our predictions with the actual values. And we can plot the calculated magnetic moment on the horizontal axis and the predictions of the magnetic moment on the vertical axis. And we can have this dashed line to be the perfect prediction line. It's not a fit, it's just a perfect prediction line. Because all our training data and our test data are falling close to this perfect prediction line, we can claim our model accuracy is pretty good. That's for magnetic moment, because we want to make these materials in the lab eventually and have them be some part of a device that helps some industry. We care about the formation energy and the chemical stability. And in this case, we can plot the calculated formation energy on the horizontal axis, the prediction of the formation energy on the vertical axis. And again, this dashed line is a perfect prediction line. Because all the points are falling close to the line, the model is performing pretty well. Happy with that? So I claimed earlier that if we add more unlabeled data, yep.
The DFT simulations themselves in need of validation by other more expensive methods.
Yes, that is absolutely true.
And would you compare the delta error, the improvement of accuracy by the error from DFT versus something more fine scale versus this error here? Like would that be a big effect, in other words, compared to the error?
It can be. It's hard to quantify it. So for predictions of formation energy, you pretty much trust those at let's say cheap flavors of DFT. And if you go to more expensive flavors of DFT, which aren't amenable to high throughput calculations, calculating very many hundreds of materials, you get a better accuracy, but you can't do very many calculations. For formation energy, you're pretty much fine. But for predicting magnetic properties, it's notoriously difficult. Sometimes, depending on materials class, it fails entirely, and it just really doesn't work. And you have to do more sophisticated things at the very beginning, include on-site interaction parameters for lattice site to compensate for the approximations of the first principles calculations, and then you start getting reasonable results. But in the end of the day, you want to compare this to like experimental data. So you compare your DFT results to the experimental data. That's the ground truth here.
Right.
Well, not here, but for the goal is to have some DFT calculations, get some idea of how the material should behave, then check the result in the lab. Did that answer your question?
Well, partly, I guess the question is whether including in your training data some of the more expensive simulations that might not even be DFTs could then help you do a better job on the final prediction, which is to experimental data.
Yes. I haven't done that, but people have reported doing that and they got improvement in their results. Yeah. Any other questions? Okay, so you can plot unlabeled data on the horizontal axis and model performance on the vertical axis. And if you start with 700 labeled points, which is a bit zero unlabeled data, which is here, your model performance is fairly mediocre, like really mediocre. And if you start increasing the amount of unlabeled data, you start getting an increase in the performance to something that's actually pretty good. So this is really remarkable. So the idea is if you improve this part of the network by adding more and more unlabeled data without doing any additional calculations, you can improve your performance by quite a bit. Something that's actually not really useful, something that gets you some predictive accuracy for materials exploration. That's nice, very nice result. That's because the autoencoder is learning the right representation for the data. And actually, one more point, because the loss functions are coupled, these networks are coupled, the loss function, the representation learned is tuned for this particular learning task, which is really neat. And also, you can play a trick where you don't learn magnetic moment, information energy separately. You can learn them at the same time. And if you do that, you can strain the model training even more, and you get a more accurate prediction with less overfitting.
So the autoencoder, do you do anything to make sure that the representation kind of spans the space as much as possible? The autoencoder doesn't really care about spreading the representation. It could put some of the data in a tiny ball and some in a large ball. Doesn't really care.
Right.
And might completely miss part of the space.
We haven't done that. That's something that we want to work on next. So we tried this, it worked. So we're happy, so we moved on. But you can do things where you make sure the points in latent space are embedded in the right way using certain techniques. I forget, CLM comes to mind, or variational encoders, for instance, and that would be an improvement over this setup. And variational autoencoders in particular, because you can start doing things like generative modeling, and I'll touch on that a little bit. I don't do that. We haven't done that yet. We want to do that next. And there's an interesting point related to that towards the end. Any other questions? Okay. So it's like magic. Really, it's really fantastic that this works as well as it does. Okay, so what you can do next is collect your DFT calculations and your AI predictions and start doing screening by selecting certain values for your magnetic moment and certain cutoffs for your formation energy, and then going from a large set of candidates to a small set of candidates to find then some key materials which might be of interest for further investigation. And that could be comparing the predictions with additional DFT calculations, which we did, and found that our predictions are pretty close to our validated DFT calculations or DFT validations or first principles validations. And then the next step would be then picking a material of interest and having to do synthesis and experiments on these materials, which we haven't done yet. Okay. The physical insight part, you can then take your latent space of your autoencoder and project it into 2 dimensions to make a nice plot like I did here. And this is a first PCA component, second PCA component. The color is magnetic moment. So blue is the 0. Maybe it could be probably they're anti-ferromagnets in the 0 here. And in the red, they're ferromagnets with a large magnetic moment. You notice in this part of the projected latent space, they're all ferromagnets. As you go from here to here, you start getting higher and higher magnetic moments. The highest ones exist in this space. So you can imagine if you had say a variational encoder or set up to do generative modeling, you go to this part of the space and then decode what that material should be and find another material with a really big magnetic moment potentially. We haven't done it yet, but that's an idea for the future. So, but the point is, the model here is learning the structure property relationships. Clearly, the structure is encoded in the input, which is then somehow encoded in latent space. And you project it to the 2 dimensions. You can extract a mapping between the structure, some transformation of the structure to the magnetic properties, which is kind of interesting. It's hard to get physical insight from this particular approach, but there are ways you can maybe massage this to get some insight from it then. Okay, so that's the first part. So I'll go quickly through the second part and then also through the third part. It'll be fairly quick. So we can do something similar for these van der Waals topological materials based on manganese bismuth telluride. Playing the same game. By the way, most of this work was done by a talented postdoc, Makanta Bhattarai, who unfortunately recently left the group and joined another group at University of Massachusetts at Lowell. Anyway, he led these calculations. He took this manganese bismuth telluride crystal. Manganese atoms are here. Bismuth atoms are here. Tellurium here, 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 and here. And he would decorate the manganese bismuth telluride tellurium with different atoms, different transition metals, like tin and antimony for B sides, different chalcogens for the X sides. If you do that, you get about 10 to the 4 possible candidates. He chose only 180 to do DFT calculations on, and did a similar thing where he would create a data set, build some scripter space, build an AI model, and predict the rest of the space using these AI model trained on only a couple hundred data. These materials are interesting because they have exotic electronic behaviors, so-called topological and so-called topological properties. Some of them are topological insulators and so-called Chern insulators. They have applications in spintronics, so think microelectronics with higher energy efficiency, novel quantum computing architectures, and dissipation electronics. Pretty exciting potential applications. So same game, taking a lattice, decorating the slides with different traditional metals, here, different atoms here, different atoms here, create a data set of materials. These are some of the results from DFT. This is the magnetic moment. Magnetic moment is like the magnetization of the material. Again, there's a pattern in the data, and we like the model to learn the pattern for quantitative predictions. We did that with a simple machine learning model. I think we used an XGBoost classifier or XGBoost. I forget exactly what it was, but not a neural network. And we can plot the calculated magnetic moment on the horizontal axis and the predictions on the vertical axis. Again, this dashed line is guided to the eye. And for material search purposes, the model is working pretty well. We can then do some screening, selecting criteria for finding a good set of materials, and then make a model to predict both formation energy and magnetic moment, quickly generate a large set of interesting materials and their corresponding properties, and then find the best candidates, and then check the results with additional DFT. We found good agreement with our machine learning predictions and our DFT or first principles calculations validations. But for the last part, we can then do this for heterostructures of materials. In heterostructures, it gets kind of exciting. So these are when you have your 2D material, you stack different kinds together, create a heterostructure with the potential to have maybe some tuning of materials properties, which you can't do with just combining atoms together in a crystal. So the combinatorial space becomes really enormous. And in this case, I constrain my materials, my 2D materials to, I think, 1,000 or a couple thousand, which is not unreasonable, because before we found that you could be as high as 10,000 for a particular crystal structure type. And if you include maybe 3 or 4 layers, you get about 10 to 26 candidates, really a large chemical space of these 2D heterostructures. So having a tool like AI help us figure out where to focus our material search is invaluable. We played a similar game. We looked at manganese bismuth telluride for one layer, bismuth telluride for another layer, and we would then change the chemical composition of the different sites, do some DFT calculations on a small set, and try to predict on a much larger set of materials using our AI tools. And these materials are also important for applications in spintronics and topological quantum computing and dissipationless electronics. So we put this MBT for one layer, bismuth telluride for the other layer, decorate the sites by substituting the manganese, different transition metals, bismuth with different elements here, and the calculagent tellurium, different elements here, sulfur, selenium, and tellurium. Then you get some data sets of DFT calculated properties. In this case, it was the magnetic moment. For instance, one heterostructure, manganese, chromium, tin, telluride top of bismuth selenide is here. Each square is a different heterostructure. And you can see there's some property here that's hard for us to kind of quantify at least in my mind. But you can ask a machine learning model to try to learn the pattern, learn the structure property relationship for quantitative predictions. So we did that, and it worked remarkably well. If we plot the calculated magnetic moment on the horizontal axis and the machine learning prediction on the vertical axis, again, this gray dashed line as a guide to the eye, we can find that our model is working pretty well because all the points for both for training and test data are falling close to this line. So we can again do some screening, selecting some search criteria, using your model to really quickly estimate the properties of a vast set of different heterostructures to find those that are interesting for us, and then check the values with additional DFT calculations. We found that it worked pretty well for the materials we were interested in, which is really nice. Okay. So to summarize, we did semi-supervised learning of a study of a set of transition metal halides. Then we applied these techniques to do a screening of topological van der Waals magnets. And lastly, we applied this to a set of van der Waals magnetic heterostructures, which had enormous search space. This work creates avenues for understanding emergent behavior of materials, or spin and charge properties, by combining these material studies of spin properties of materials with AI. And we have a way to really accelerate technological innovation by finding the right materials with the right properties for a particular task. Outlook is to use these approaches for different set of crystal structures, looking at different properties with other exotic spin and charge degrees of freedom, like skyrmions or so-called spin textures or ultramagnets. If you haven't heard of that, that's a really exciting new material emerging. Or maybe something that's already known, like superconductivity. We use these approaches to look at find new superconductors. Search space can be enormous, so having a guide, which is AI, to find these materials for this right task is really important. One last thing I want to say before I close is that I said often in classical simulations of quantum systems, quantum materials, very recently at RPI, we have the IBM Quantum System 1, which is just I think the only, how should I say this? Not the only quantum computer, but the only, what's the word looking for? Quantum computer provided by a company exists at RPI that's on a university campus. And we were trying to study spin properties of these systems by doing quantum simulations. And we're having a project on simulating quantum spin liquids, and we'll try to improve our DFT calculations by using these quantum simulations in the future, improving on classical DFT using these quantum systems to get better calculations. But that's a kind of in the works project, but very exciting. So we'll couple quantum computing with classical computing alongside AI together to make really a nice synergistic effect for materials discovery. If you want to learn more, please take a look at this QR code to see this paper in Advanced Theory and Simulation. I'd like to thank Access, formerly known as XSEED, ALCF, and SF Career Award. I'd like to thank you for your attention.